Now let's continue. All right. So in this specific section, we would like to introduce how we basically use the theory of constraint to manage within the line process. All right. So first of all, here, as you can see, within the whole line process, all right, definitely we will include a few different sequential tasks that we have to include in order to, for example, produce a product, in order to, provide a service. All right. And here we would like to basically use a number of workstations and let them work simultaneously. All right. In order to basically complete the target of number of products or provide enough service within a very limited time. Okay. So that basically is core meaning of line balancing. All right. Here, as I said, since this line process will include a few different sequential tasks, all right, so we basically within the information context, definitely we would tell you, for example, we need to complete task A before we can start task B, and then we need to complete task B and task C before we can start task D. All right, so all this information will be given. But here, in order to get a better sense about the whole structure of the production process or service process, right, we further introduce a diagram called precedence diagram. And this diagram will basically allow us to visualize the immediate predecessors better. Now let's continue. Here, I basically provide a few simple examples about the precedence diagrams, which only includes, for example, 3 different tasks or 4 different tasks. All right, now let's start from the first example. So in this example, you only have S, T, and U, these 3 different tasks, all right? And in this structure, okay, if we have this structure, it basically means that you have to first complete S before you can move to task T, before you can actually start to do task U. Now let's move to the next example. In this structure, all right, the core idea is very straightforward. You have to first complete both task S and also task T before you can start to work on task U. All right, so that would be the core idea of this structure. Now, if we move to this specific structure, we still include task S, task T, and also task U. But here, as long as you complete task S, you can start to work on either task T or task U. That's the core difference here. All right, now let's move to some kind of variations by having 4 different tasks. All right, for example, the first one. This one is a very symmetric structure. All right, so here basically you have to complete both task S and also task T before you can start to work on both task U and task V. Okay, here if we move to this structure, all right, so in this specific structure, in order to start to work on task U, you have to complete both task S and task T because you have both arrows from S to U and also T to U. All right. However, in order to start task V, okay, as soon as task T is completed, you can actually start to work on task V. So that will be the difference between task U and task V. All right. Now here, this will be another structure, but the underlying logic is exactly the same. All right. First of all, you have to first complete task S. After you complete task S, you can consider start working on task T or task U. All right. However, in order to start working on task V, you have to complete both task T and task U. So this will be just a simple illustration about different type of structures for precedence diagrams. All right, now let's continue. Now let's use one very straightforward, very important example to illustrate the line process. So for example, we are a company, all right, and we're manufacturing lawn and garden equipment, all right, and which is basically designing an assembly line to produce a new fertilizer spreader, all right. And the following basically are some very important information about our production process. And we try to construct a precedence diagram for the big broadcaster. All right, now you can clearly see that within this specific table, all right, here, in order to produce the product, we actually include a few different work elements, starting from A until I, as you can clearly see this. All right, and for every work element, it actually has the corresponding description. Okay, and also we have the specific time that we have to spend in order to complete that specific work element. All right, now the most important thing is showing here, which is called immediate predecessor. Now, the immediate predecessor tells us basically in order to start every single work element, do we actually have the predecessor before that specific task or that specific work element? All right, for example, here, for work element A, there's no predecessor. Basically, we can start from working on task A. That's basically what it means. All right. However, if we continue, if we look at work element B, the immediate predecessor is A. What it means? Very simple. It indicates that basically we can start working on work element B only when A is completed. Okay, only when A is completed. Now, for work element C, still the same thing, right? Basically indicates that, okay, you can start working on work element C only when the task A, the work element A, is already completed. Now, same logic for the following work elements. Okay, for example, for work element D, it indicates that, okay, basically only after you complete task B, you can start working on task D. Okay, or let's say another example, work element H, it indicates that basically you have to complete both work element D and work element E before you can start working on work element H. Okay, that's why here, if we plot out the corresponding diagram showing here, all right, we start from building up work element A, right? And then we have an arrow to work element B and also work element C, because work element A is immediate predecessor for both work element B and work element C, which is showing here. Okay, and actually for work element D and E, we know that actually the immediate predecessor is work element B, showing here, right? That's why here you see both D and E is after B. All right, and similarly, we know that basically for work element F and G, the immediate predecessor is work element C. That's why you see here for F and G, right? This is after C. Okay, now if we continue to look at work element G, since the immediate, if we look at the work element H, you can see that the immediate predecessor should be both D and E. That's why here, see, only after you complete both D and E, you can basically start working with H. All right. Similarly for I, you see that the immediate predecessor are both F and G. That's why here, after you complete F and G, and then finally we can start working on the work element I. All right. So this will be a quick illustration about how we plot out the precedence diagram. Now let's continue. After we know how to basically plot out the precedence diagram, then we need to start to think about, we need to build up how many workstations such that we can actually assign those different work elements into different workstations and let those workstations work simultaneously, such that we can actually save some time during this whole production or service process. And then we can basically produce enough products and also provide enough service within a limited period of time. All right, now here I provide a few very important equations here. Let me briefly introduce every one of them, and then I'd like to use a great example to give you guys a better sense about every single equation. The first equation that we will introduce is related to the cycle time. Basically, cycle time here is representing the maximum time that every workstation can spend in the process of producing every single unit or providing each service. All right, so this would be very straightforward. All right, and then after we understand cycle time, then we move to the theoretical minimum number of workstations equation, which is actually very straightforward. Here, as we know, if we do not actually include any workstation, okay, if we basically complete all those different tasks one by one sequentially, all right, then we have this total amount of time in order to complete, let's say, every unit of product, or to complete every single service. All right, divided by the cycle time basically is the maximum amount of time every workstation can spend in the process of producing every single unit or providing every service. And then the result will give you the theoretical minimum number of workstations that we probably need in order to complete this production process or complete this service process. Okay, now let's move on. The third equation is related to idle time. All right. So here, as you can see, idle time equals NC minus summation T. What it means? Very simple. N basically represent number of workstations that you are using within this production process or service process, right? C basically represents the cycle time. So that's why here, if you use N times C, that's basically is representing what is the maximum amount of time that are included within this whole process by having this specific amount of workstation. Okay, this is a little bit like the capacity amount of time for your production process or service process. Summation T basically is representing the total time that is necessary or that is required in order to complete every single unit of product or in order to complete every service. Okay, so that's why here, if we use NC minus summation T, that will basically give you the time that is remaining that is not being used within this whole process. Okay, similarly, if we move to the equation for efficiency, you see that actually at the right-hand side, we still have these two elements, right? In the numerator, we have summation T. This is still representing basically the total time that we are required to use in order to complete every single unit of product or every single service. The denominator is still NC, basically it's representing, okay, what is the maximum amount of time that actually we have by having all these different workstations within the whole production or service process, okay? So that's why here, if you use summation T, divide by NC and times 100, that will give you the corresponding efficient percentage. Normally, the efficiency percentage will be below 100%, okay? So let's use a quick example to illustrate those equations that we just mentioned. Okay, very simple. Now, Greengrass plant manager just received marketing's latest forecast of big broadcaster sales for next year. All right, and she wants this production line to be designed to make 2,400 spreaders per week for at least the next 3 months. And the plant will operate 40 hours per week. What should be the line's cycle time? Okay, now, in order to calculate the line cycle time, it's actually very straightforward here. Since we already know that basically the company wants to basically make 2,400 spreaders per week, and we know that the plant can only operate 40 hours per week. All right, so in order to fit for the market demand, which is 2,400 spreaders in this week, all right, then we know that basically for every spreader, if we want to produce it on time, right, the time that actually we can spend on that specific spreader will be 40 over 2,400. That's why if you look at part A, the basic solution I show here, right? If you use 40 over 2,400, that would be equivalent to 1 over 60. And the corresponding unit would be hour over unit, basically hour per unit, okay? But here, if we want to consistent our unit, okay, with the previous information as we show here, okay, as we show here. All those things actually show here is using the second as the unit of time, right? So that's why here, we know that the corresponding unit for a 1 over 6 is hour per unit. So if we want to further translate it to second per unit, it's actually very simple, right? 1 over 60 hour per unit is equivalent to 1 minute per unit. Is also equivalent to 60 seconds per unit. So that's why here we already know that basically the cycle time is 60 seconds per unit. This should be very intuitive. All right, now, after we know the cycle time, we then can calculate what is the smallest number of workstations that basically we can hope to design within the process line, okay, by having the cycle time. Very easy. We know that, all right, within the previous example, okay, we already know that if we sequentially produce every single work element, you know, one by one sequentially, then the total time that we need to spend is 244 seconds. But of course, here, in order to fit for the market demand, right, for every single unit, we can basically only use 60 seconds for that specific unit, all right? And that's why we need actually multiple workstations to work simultaneously in order to fit for that specific requirement. Now, we know that the total amount of time that we need is 244 seconds. Okay, this is the required amount, all right? And for every workstation, the maximum amount that we basically can use is 60 seconds. Then how many workstations we need to build? Very simple. We directly use 244 seconds over 60 seconds. Okay, they will give you here directly, it would be 4.067. However, since this is related to the number of workstation, then we need to run up to 5 stations. So that's why theoretically, okay, the minimum number of workstations that we need is 5 stations. Now let's move to the last part of this specific example. So suppose that the manager finds a solution that requires only 5 stations. What would be the line's efficiency? In order to figure out the efficiency for this whole process, actually very simple. All right, here we know that efficiency equals to the total requirement time divided by NC. Basically, it is expressed as the total capacity time that actually we can use by having this number of workstations, right? Very simple. Now, we know that basically the total time that actually are required to use in order to produce a product or providing a service is 244 seconds within this specific example. Now, suppose we already find a 5-station solution, which indicates that basically the number of these workstations that we will use within this whole process will be 5. All right. And we also know that basically the maximum amount of time that every workstation can use is 60 seconds. So that's why here, by having 5 times 60 seconds, that will give you the maximum capacity time that 5 workstations can use, which is 300 seconds. Then you use 244 divided by 300 and then times 100. That will give you the corresponding percentage that basically we use during this whole production process. That's why here, this is corresponding to the concept of efficiency. Okay, so this would be pretty much the order of the content that we will cover within this whole chapter. If you have any question, feel free to let me know. Thank you.